let's start with something super simple. Let's start with a box, right? And you already talked about this. We've already drawn this free body diagram. We drew it with a rock. And so I'm just going to abbreviate the types of forces. So this is the force of gravity, pulls down on the box. And then we get the normal force, the support force that holds the box. Now, when I look at this, the up force equals the downward force. This means I'm in equilibrium. This is sort of a Newton's first law thing, right? An object at rest will rest unless acted upon by a net external force, meaning that the sum of the forces is going to be equal to 0. So if I ask you, what is the magnitude of the force? Well, I sum my forces, and in this case I only have one direction. I only have the y direction, but I'm going to go ahead and just say I sum the forces in the y direction. That's going to be equal to 0 because I'm in equilibrium. So the sum of the forces in the y direction equals 0, which means the normal force minus the force of gravity is going to be equal to 0. Or I can move this to the other side. The normal force equals the force of gravity. If you remember from the other day, the force of gravity also means the weight. This number does not change unless you go up to the moon or somewhere else where the gravity field strength is different. So the weight of an object is just mass of the object times gravity. So let's say that this is a 3 kilogram box. A kilogram is about 2 pounds, 2.2 pounds. So this is like what, 6.5 pounds, 7 pounds. So the weight of the object is the mass of the object times gravity. And so my normal force is mg then, because it equals the force of gravity, which is 3 kilograms is 10 meters per second squared. Now this is sort of weird because I get 30 and then I get this weird unit, kilograms times meters over seconds squared. But this is the normal force. When we talked about forces the other day, I gave you a unit for a force and I gave you the unit as newtons. The force of an object is given in newtons, and so this weird unit here, kilogram times a meter per second squared, this is a complicated way of writing newtons. So that's actually what a newton is. It's sort of interesting. So this is just going to be 30 newtons. Okay, how would this change if I put, I'm just going to be super not fancy, if I put a triangle, some sort of pyramid, on top of the box? Okay, so now things are getting a little bit more complicated because I have a box and I have a pyramid. And so when I draw a free body diagram, I want to make sure that what I'm drawing the diagram of. I'm going to fold this up. It's pretty easy to think about the free body diagram of the triangle. And let's say the triangle has a mass of 2 kilograms. So the free body diagram of this is just going to be, again, the force of gravity going up and the normal force coming down, right? This is the free body diagram of the triangle. All of the forces that are acting on it. Now that we look at the box, these two are not the only forces on the box anymore. So I'm going to X this out. We're going to draw a new free body diagram. We'll draw it right here. So the force of gravity on the box hasn't changed, right? You still get the same force of gravity because the mass of the box hasn't changed. But now we have the triangle that's sitting on the box, and that triangle is pushing down on the box. It's applying a downward force. And so we get another force downward. And this force here is going to be the force on the box by the triangle. And then we still have that normal force pointing upward. Now, how big is that normal force going to be? That's our question, right? And I drew extra big because the sum of the forces in the y direction are going to be equal to 0, meaning the downward is equal to the upward force. And because I have two downward forces, that's going to be equal to a bigger upward force. So the sum of the forces in the y direction, this is going to be, again, we're going to look at the box. And so I get the normal force going up minus the force of gravity, and I'm going to say that that's the force of gravity on the box, minus the force on the box by the triangle. Now, let's rename a couple of forces over here. Okay, I'm going to use some on-by notation. So this is the force on the triangle by the earth, right? The upward force on the triangle is the force on the triangle by the box, because the box is the thing that's holding it up. So notice I have these two forces. I have the force on the triangle by the box, and I have the force on the box by the triangle. These forces should sound sort of familiar. Notice how their labels are flip-flopped. That means that these two forces are third law pairs, that these two forces are going to be the same size, but opposite in direction. Okay, so how big is this force on the box by the triangle? Well, it's going to be the same as the force on the triangle by the box, which the triangle isn't moving. The triangle is in equilibrium, so this upward force is going to be equal to this downward force, and so the force on the triangle by the box is going to be equal to force of gravity on the triangle. And so these two forces are equal. They're both the force of gravity on the triangle. And so this is also going to be the force of on the triangle. Okay, so where does that leave us? Equals 0. So I'm going to pull, this time I'm going to pull these two things to the other side so that we don't have any weird negatives. So the force of gravity on the box plus the force of gravity from the triangle equals the normal force. And so remember, the force of gravity on the box is the mass of the box times the gravitational field strength, and the force of gravity on the triangle is just the mass of the triangle times the gravity, the gravitational field strength, and that's going to be equal to the normal force. And so the mass of the box, 3 kilograms times 10 meters per second squared, plus the mass of the triangle, 2 kilograms times 10 meters per second squared as the gravitational field strength, equals our normal force. So 30 newtons plus 20 newtons is the normal force, or 50 newtons, which is why I drew this force as being bigger than these two, because it is the sum. This is going to be 50 newtons, 20, 30.